Our world is held together and supported, but no, not by three pillars like some myth might suggest. It actually stands firmly on just two fundamental pillars. Everything around us is sustained by the electromagnetic field and by gravity, working together at every level. If you were to remove the electromagnetic field, atoms themselves would cease to exist and the entire structure of matter would collapse instantly, like a fragile castle built on sand. If gravity were removed instead, all the enormous structures built upon those atoms, in other words, the entire universe as we know it, would begin to fall apart. Stars would never form, galaxies could not hold themselves together, and everything would eventually scatter and drift away as dust. The quantum of the electromagnetic field, known as the photon, has already been captured, studied in depth, and successfully harnessed in modern technology. Gravity, on the other hand, has remained frustratingly out of reach for a very long time. Gravity clearly governs the entire universe, yet no one has ever directly observed its quantum particle, the graviton. So what exactly is going on here? It has long been considered something fundamentally invisible, something that, in principle, could never be tested through experiments. Hello everyone! But now, that long-standing situation is finally beginning to change. Physicists are seriously exploring the possibility of building real experimental setups that could verify the quantum nature of gravity, not just in theory, but right there in the lab. Welcome to our channel. Let's dive in and take a closer look at all of this together. Why we can't see it. 10 to the power of 42 reasons. It's true, we've spent a very long time studying the electromagnetic field in extraordinary detail. That field has its own quantum particle known as the photon. We've learned how to detect it, count it, manipulate it, and even build entire technologies on top of it. So logically, if gravity is also a field, then it should have its own quantum particle as well. That hypothetical particle has been given a name, the graviton. If it really does exist, then the photon would no longer hold its status as the only particle of its kind. Right now, the photon is the only freely observable particle known to travel at the speed of light and have no rest mass. The graviton is expected to share those same exact properties. In other words, it would be a particle with zero rest mass that carries the force of gravity itself. It's a bit ironic, like a craftsman who never gets to use his own tools. The real problem is that this particle has never actually been observed. So, why is that? The reason is simple but extreme. Gravity is unbelievably weak. Between two electrons, the electromagnetic force is stronger than gravity by a factor of 10 to the power of 42. Just try to wrap your mind around that number for a second. At the level of elementary particles, gravity is so faint that it's practically undetectable and often ignored in calculations. At one point, the hardest particle to detect was the neutrino. To catch even a few of them, humanity had to build facilities on a truly enormous scale. And yet, compared to the graviton, the neutrino looks like a rookie standing next to a seasoned pro. Detecting a graviton would be like trying to hear your own sneeze in the middle of a roaring hurricane. To capture even a single one of these quanta, you would need a detector the size of an entire planet. Not Earth-sized either, something on the scale of Jupiter. And the event you would need to observe wouldn't be anything ordinary. You would have to wait for two black holes to collide and merge. And even then, the experimenter would need a lifespan like Duncan MacLeod, the immortal hero from the TV series Highlander. Put simply, the difficulty of this problem almost seems intentionally cruel. We actually understand quite a lot about what this particle should be like, its speed, its spin, and the fact that, in theory, its mass should be zero. But the chances of ever capturing one are so small that they might as well be zero. And yet, has that ever been enough to stop human ambition and curiosity? How can we outsmart the weakness of gravity? A few years ago, a more refined and surprisingly clever idea began to take shape. Instead of trying to detect a graviton through a direct exchange of momentum, which would show up as an almost imperceptible mechanical kick, the idea is to let the graviton excite the quantum state of a large macroscopic system instead. Imagine a metal cylinder made of materials like beryllium or niobium. Now, cool that cylinder down to temperatures extremely close to absolute zero. Cool it so far that nearly all thermal vibrations are effectively eliminated. In this extreme state, the collective vibrations of the metal start to behave according to the rules of quantum mechanics. They no longer occur as smooth, continuous motion, but instead happen in discrete, sudden jumps. Each one of those jumps corresponds to a photon, a quantum of vibrational energy. The idea is that a graviton with just the right frequency could transfer exactly one quantum of energy into the system. When that happens, a photon would be excited. And in principle, modern quantum sensors are sensitive enough to detect a jump of that kind. So rather than trying to catch a graviton directly, the proposal is to record the system transitioning from one quantum state to another. But almost immediately, a serious problem appears. Phonons are not excited exclusively by gravitons. Thermal noise, seismic vibrations, electromagnetic interference, all kinds of background disturbances can produce the exact same effect. The energy carried by a single phonon is incredibly tiny. Completely eliminating noise is, in principle, impossible. In chess terms, this is a check, but it's still far from checkmate. That's where the next move comes in. Since 2015, detectors like LIGO have been recording gravitational waves, ripples in spacetime produced by mergers of black holes and neutron stars. If gravitons do exist, then a gravitational wave would essentially be a massive stream of gravitons moving in perfect phase together. And all of them should share the same frequency. So the trick is to tune the natural vibration frequency of the cylinder so that it matches the expected frequency of those gravitational waves. Then, at the exact moment LIGO detects a gravitational wave, if a quantum jump occurs inside that cylinder, it would be powerful evidence of an interaction with gravitons. It wouldn't be absolute proof, not a final checkmate, but it would come incredibly close. Experiments near absolute zero. From a technical standpoint, this kind of experiment pushes right up against the very limits of what modern physics can achieve. But the approach itself operates on a completely different level compared to anything that came before. Not long ago, it was widely assumed that detecting a graviton would require an apparatus weighing thousands of tons. Quantum mechanics, however, offers a far more subtle and elegant strategy. Instead of brute forcing the problem with sheer mass, the idea is to take advantage of resonance. And when you think about it, that sounds a whole lot more manageable, doesn't it? So let's take a closer look at how this would actually work. Gravitational waves produced by merging neutron stars typically have frequencies in the range of a few hundred hertz, which is why physicists are proposing the use of acoustic resonators. You can picture this as a precisely engineered metal bell, crafted from materials like beryllium, niobium, aluminum, or even single crystal sapphire for maximum performance. The mass of such a device could range anywhere from just a few kilograms to several hundred kilograms. That puts it firmly within the scale of laboratory equipment, something that can realistically be housed inside a cryostat. And this is where the real challenge begins. To detect a quantum jump, meaning a transition of the system from one energy level to another, you have to eliminate almost all sources of thermal noise. That means cooling the system down to about 0.001 Kelvin, which is just 1 millikelvin above absolute zero. For comparison, the temperature of the cosmic microwave background is about 2.7 Kelvin. In other words, you would need to create an environment thousands of times colder than intergalactic space itself. Even modern commercial cryostats can only cool down to about 0.01 Kelvin, which is still 10 times higher than what this experiment requires. Let's say, for the sake of argument, that under laboratory conditions you somehow manage to reach that target temperature. Even then, that would only solve a small part of the problem. The biggest issue is that no one can predict exactly when a gravitational wave will arrive. It could happen tomorrow, or a year from now, or even 10 years down the line. And during that time, you would have to keep a device weighing hundreds of kilograms at 0.001 Kelvin, maintain it in an ultra-quiet quantum state, and monitor it continuously without interruption. On top of that, the act of measurement itself must not disturb or destroy the quantum state you're trying to observe. Light instead of a cylinder. There's also another alternative approach that's been proposed. It's something known as an optical Weber bar. This idea is so old school that it feels about as ancient as the Egyptian mummies displayed in museums in London. In the original concept, a massive metal cylinder would start to vibrate ever so slightly as a gravitational wave passes through Earth. As the wave stretches and compresses space by an incredibly tiny amount, the cylinder experiences a minute mechanical disturbance. Now, imagine replacing that metal cylinder with light instead. Here's how the concept works in practice. You use an interferometer, a device designed to measure extremely small changes using light interference. In terms of overall design, it's similar to LIGO, but the goal here is fundamentally different. LIGO directly detects how a passing gravitational wave changes the length of its interferometer arms in real time, which shows up as a shift in the interference pattern. The optical Weber bar, on the other hand, is meant to capture those fleeting ripples and actually extract a tiny amount of energy from the gravitational wave itself. The idea is to imprint that energy into the light, leaving behind a measurable trace. Even so, simply observing an exchange of energy between the gravitational field and the electromagnetic field would not be enough to conclusively prove that gravitons exist. That's because even a classical gravitational field can, in principle, transfer energy. So what if we prepare the light in a highly non-classical state, one with very unusual statistical properties? For example, squeezed light, where the uncertainty in amplitude is increased while the uncertainty in phase is reduced, or the opposite configuration. Or consider light prepared in a Fock state, where the number of photons is fixed with absolute precision. Introducing light in these kinds of states imposes extremely strict constraints on the system. Because of energy conservation, the quantum state of the light becomes directly linked to the energy state of the gravitational field. In that case, there is a real possibility of experimentally probing the quantum nature of gravity itself. A classical wave cannot become quantum mechanically entangled with a detector, but a quantum field can. And detecting that kind of very specific quantum correlation would be the true smoking gun, the decisive evidence everyone has been searching for. Did we catch it? Not so fast. Now imagine this. One day, one of the detectors we just talked about finally records the long-awaited signal. A quantum vibration is captured, or the optical Weber bar measures the energy transferred from a gravitational wave into light. The millions, even tens of millions of dollars invested in the experiment have finally paid off. Graviton detected. Except it's not that simple. The problem is that the exact same effect could also be produced by a classical gravitational field. A classical gravitational field can deliver energy at the required frequency and increase the probability of a quantum jump in this system. Yes, we would observe transitions between discrete quantum energy levels, but that doesn't necessarily mean the energy arrived in the form of individual gravitons. A single isolated detection would be extremely compelling evidence, but it still wouldn't be the final blow against classical gravity. Even so, it would shift the discussion out of the realm of philosophy and firmly into the domain of experiment. After all, even in the case of the photon, there was no single experiment that proved everything at once. The evidence built up gradually over time. In science, breakthroughs rarely happen with a single decisive strike. More often, the conclusion emerges through a steady accumulation of wins on points. For now, all we can really do is wait. And chances are we may be waiting for quite a long time. That's because the experiments we've been discussing still exist only at the conceptual stage. There are no concrete timelines and no clear budget estimates yet. Even so, this represents a truly significant step forward. If you found this video interesting, be sure to leave a like and share it with your friends. Thank you all so much for watching. We'll see you again soon. Goodbye.